morning, everyone. I welcome everyone for day 8, lecture 20 session, I can say. The title of today's presentation is Chemical Kinetics and Mechanism for Ammonia Formation. There are two things we are going to study, I can say, discuss today. One is thermodynamics and is the chemical kinetics. What is the role of thermodynamics? Then chemical kinetics in forming from the products from the reactants. So learning objectives, understand the fundamental principles of chemical kinetics, such as reaction rate, reaction order, reaction mechanism, and activation energy. Explore the effects of the plasma parameters, power, frequency, etc. on reaction kinetics and ammonia yield. Discuss how catalysts lower activation energy and increase the rate of ammonia synthesis. Explain how modifying reaction conditions or using advanced catalysts can improve the rate determining steps in ammonia synthesis. Assess the potential impacts of innovations in reaction mechanisms and kinetics on reducing carbon emissions in ammonia synthesis process. So the presentation falls under 5 categories: fundamentals of thermodynamics and kinetics, reaction mechanism in ammonia formation, mechanism of catalyst action in reducing activation energy, comparison between plasma-assisted and traditional catalytic methods, industrial challenges and future directions in ammonia kinetics research. So all we know that the first law, that we have, I can say, 4 laws of thermodynamics. Thermodynamics the word derived from the Greek therm. Therm means heat. Dynamics means power. So the study of heat and power. And that's the reason why we are producing the heat from the different sources and how this heat is going to be converted by using some devices. Similarly, we are going to apply some system where the work can be converted into heat. The good example is electrical heater, geyser, wherever I can say the work is converted into heat, then you can think about, I can say, this other form of energy transfer. We are going to study the 4 laws of thermodynamics: 0th law, 1st law, 2nd law, and 3rd law. The 0th law, we are going to study the temperature, the equilibrium, we can say. You maybe all knowing that when 2 systems are in equilibrium with the 3rd body, I can say definitely all 3 bodies are in equilibrium with each other. Okay. So the fundamental from the 0th law of thermodynamics, we found the property called temperature. Then the other next law is the 1st law, is the conservation of energy principle. Energy is neither created nor destroyed, it will be converted to one form to another form. So it is not going to be in a, I can say, it's not going to be stable. So if you want to disturb the system, naturally it has to go from one form to another form. The good examples of 1st law is the potential energy is converted into mechanical energy, or I can say in the steam turbine you are converting heat energy into mechanical energy. In the internal combustion engine you are converting chemical energy to heat energy, followed by heat energy to mechanical energy. So different forms of energy transfer happens. But if you see the total energy transformation from input and output, all the inputs and all the outputs going to be remain same. From the 1st law, we are come with I can say the concept called energy. Then from the second law of thermodynamics, there are some limitations are there in the first law because it doesn't talk about the direction of energy flow. Doesn't talk about the we are saying knowing that okay this much 100 kilojoule of heat is available, 100 kilojoule is converted into I can say kilojoule of heat converted into work. 100 kilojoule of work is available is converted into 100 kilojoule of heat. But from which point to which point the energy transferred. So that is missing in the first law of thermodynamics, and also we are the degradation of energy also not taken into account for the first law of thermodynamics. Then we are going to find the I can say they have found the next law. It's called a second law. They are saying that entropy of an universe is going to be I can say always increases. Because you all know that heat you are pumping into the surrounding naturally the entropy is going to be increases. Entropy is nothing but the measure of disorder or randomness of the molecule. When the process happens, then there will be a always we can say there will be an energy rise happens at the upper end of the process. So from the second law, we come across with so from the second law we come across with two statements. One is called Kelvin-Planck statement, another is called Clausius statement. Kelvin-Planck statement talks about, I can say, that it belongs to the engine. As you all know, that engine is a device which can convert the chemical energy of the fuel into heat energy to the mechanical energy. So, in the Kelvin-Planck statement, they are telling that without rejecting heat to the surrounding, you are not able to produce the work. So that means what first law says is the total heat is equal to total amount of work produced. Right? They doesn't talk about the energy dissipation. Okay. So here the second law talks about amount of heat supplied is equals to amount of work coming out from the system plus amount of heat rejected to the system. The good example you can say is the internal combustion engine. You are producing heat from the fuel. The fuel is the chemical is stored in the fuel. During the combustion, you are converting chemical energy to heat energy. Whatever be the amount of heat available from the products of combustion is going to be, I can say, some percentage will be converted into work, then the remaining percentage will be converted into, I can say, heat. That is going to be rejected. Without rejecting the heat, you cannot be able to produce the, I can say, work. So what I mean to say in second law is 100% conversion of work to heat to work is not possible. Some amount of heat has to be rejected. Then the Clausius statement in the second law they talks about, I can say, that is belongs to refrigeration or heat pump, unless otherwise the work is provided into the system, I can say you cannot increase the temperature of the particular system, which is more than the surrounding temperature. So thermodynamics. The most important subject in I can say mechanical, electrical, or energy department. It's derived from the word term. So there are few scientists who really contributed for the thermodynamics. I can say Carnot, I can say Kelvin, Clausius. Right? There are many people they have contributed I can say thermodynamics based on their invention and innovation, and we are able to understand the concept of thermodynamics. There are I can say the zeroth law. The zeroth law. We are finding out the property called temperature. That is the basis for finding out the temperature. So here, even I can say when the body A and B is in equilibrium with the third body, automatically all the bodies are in equilibrium with each other. For any reaction, I can say to form, I can say hydrogen reacts with hydrogen, the presence of some amount of energy, heat or pressure are going to produce ammonia, right? So any reaction, you can say, the temperature plays a major role. Temperature, because the Haber-Bosch we are saying that So in order to, I can say, produce the ammonia, you need to maintain the temperature of 500 degrees centigrade, temperature of about 300 bar, right? So the temperature plays a major role. So in order to know the, I can say, the parameter temperature and who has really contributed in, I can say, finding the property that comes from the zeroth law of thermodynamics. Then the first law is a law of conservation of energy. How much is available is going to be spent. Suppose you are having 100 rupees, that has to be spent, that has to be reached to someone after some time. Okay. Then the second law is the most important law where we are going to talk about the property called entropy. The property entropy is arrived from the, I can say, the second law. First one is Kelvin. What this law talks about is, you have a system, assume that this is applicable for heat engine, H. You are having a source where you are going to provide the heat at a temperature Ts. You are going to reject some amount of heat to the sink, normally we call it as the surrounding. That is, I can say, the source or the sink. Yes. So in order to, and the amount of heat rejected is QR. The work coming out from the device, nothing but net work. So if you are providing, assume that you are providing 100 kilojoule of heat, then naturally the amount of heat you are converting is not equal to W. This is the law talks about in first law. This is the energy transformation happened in the first law, but it is not so in second law. So QS is equals to from this W net plus heat rejected. In order to produce the work from the given heat, you need to dissipate some amount of heat into the surrounding. That is called Kelvin Planck's law. So, right. So efficiency, we want to find out the efficiency of the heat engine. Symbol for efficiency is eta is equals to how much the work is coming out. Always efficiency nothing but output by input. Here output is energy in the form of work divided by energy in the form of heat. How much for a given amount of heat, how much the work is coming out. This is also equals to how much the heat I am supplying minus how much the heat I am rejecting to the company. I have basic questions here. Can you able to have efficiency 100%? First question. Second question, how much the maximum efficiency you can get? Is it possible to get 100% efficiency? So which parameter dominates in bringing your efficiency? Again, the down from 100%. Temperature, sink temperature. Now, you tell me now, how much the maximum temperature, how much the maximum efficiency I can get? The surrounding temperature plays a major role. People are saying that petrol engine is efficiency maybe around 28 to 30%. Diesel goes with 30 to 35. Where the 68% goes? We are producing 100 kilojoule of energy. Even Hyperbosch are providing some amount of energy for forming ammonia. Whether the given amount of energy, the form of heat, is going to be completely utilized for forming the ammonia. Right? So then the Conrad, the French scientist, is an army engineer who invented the cycle consuming it has the four processes, two isotropic and two isothermal. So by considering that is the maximum hypothetical cycle you can able to do it from the Carnot. He found the efficiency, maximum efficiency. So that is the ideal efficiency. You cannot get more than that. Nothing but how much the temperature is available in the source minus how much the temperature available in the sink divided by how much the temperature. So if you want to maintain if you want to get the 100% efficiency from any process or any device, you need the sink temperature, but both are in Kelvin, not in degree, both are in Kelvin. You need a 0 Kelvin. Not get 100% efficiency. You need a surrounding environment supposed to be minus 273 degrees centigrade. That means it's cryogenic. So it's not going to be never ever possible in our daily life because we are always increasing the ambient temperature. That's the reason why we are going for this workshop. Renewable energy is a concept brought in to minimize the conversion of fuel in such a way that the amount of CO2 comes out from the system is going to be coming down. Okay. So assume that the temperature, and the surrounding the source is 1000 degrees centigrade. That means assume that the heat liberated from burning the petrol or diesel fuel produces the heat of some value, the temperature is 1000 degrees centigrade. The ambient temperature is 30 degrees centigrade. Right? So what is the efficiency? Right? The efficiency of IDI. So you cannot get more than that. So 1000, that is 1000 plus 273, 1273 minus 303, convert into Kelvin, plus 273, then 1273. You may get some percentage. That is the idealization efficiency. So we are going to talk about the Gibbs-free energy, that is called the available energy or exergy we call it as. In the earlier days people are calling it in thermodynamic perspective. The chemical perspective people are saying it's a Gibbs-free energy. I can say how much I can say the energy can be recovered, how much the work can be extracted from the given amount of heat. That's called exergy or available energy. Thermodynamic perspective, for every reaction, how much the minimum, I can say how much the energy can be, I can say supplied such as the process comes to the equilibrium conditions. That's all called Gibbs-free energy. Okay. So third law, I can say, when you say entropy of, when you say entropy of system approaches constant at the temperature absolute zero. So the entropy is going to be zero because always the entropy increases. When the heat temperature increases, heat also increases, entropy also increases. If you want to bring down entropy to zero, need to maintain the absolute zero temperature. Here, we're supposed to know few energy forms other than the heat and work. We are calling it as internal energy. Assigned with the symbol U. Enthalpy H and entropy. For any process or any reaction, this is what that gives free energy. Assigned with the symbol G. So G is equals to H minus, or I can say del H minus T times. You say G equals to 0, I can say, or G is less than 0, G is greater than 0. There is a different way to do it. When you say similar to this, like del S is equal to 0, del S less than 0, del S greater than 0. Similar to this. When entropy is 0, entropy del S means change in entropy is to my final to the initial is equal to 0. That means the process is
central.
Reversible. Reversible. Yes. Reversible. What about this?
Irreversible.
This is impossible. Impossible. Yes. So this is not going to align. Entropy always increases. Right? You cannot say entropy, change in entropy is greater than 0. Impossible. So, yes, this way also here. For reaction, this is going to be equilibrium. This is called spontaneous, non-spontaneous. All the natural process come across in every day. Just in the environment is happening spontaneous. So these are the basic things you're supposed to know. Then, what is enthalpy? What is enthalpy? What is internal energy? Internal energy is stored energy. It's nothing but soda. Assume that the system is maintained at a constant volume. Whatever the amount of heat you are supplying into a system where its main volume is maintained constant, the amount of heat supplied is nothing but internal energy. So internal energy is nothing but product of mass, specific volume at constant volume times delta. We can say MCB, MCT. If you talk about the change in internal energy, you can say MCB delta T. You can say MCB into minus T. You can say here M means mass, M in kg, CV is the specific heat, in kilojoules per kg Kelvin, delta T to T1 is final temperature, Kelvin, initial temperature. Okay. Then we can go for enthalpy. Enthalpy of formation, enthalpy of reactants, enthalpy of products. Enthalpy is nothing but, is not a, I can say, measured parameter, it's a calculated parameter. It is the summation of internal energy plus flow energy. So enthalpy is abbreviated by the symbol capital H. Internal energy is U. Flow energy is the product of pressure times volume. So pressure in Newton per meter square, volume in meter. Okay. So the unit for this is enthalpy is Joule. This is also in Joule. Ultimately, if you want to find out the process is going to be, I can say, either spontaneous or non-spontaneous or equilibrium, you need to use this equation. E equal to del H minus del E times del S. So similarly, you can find out, I can say, entropy also. Other than we are finding out the entropy, we are always finding out, I can say, change in it. You are interested in change in it. Yes. So we can find out what may be the difference in the entropy after the process from the initial. So that is nothing but dq by change in, I can say, heat transfer with respect to the process. There are several processes thermodynamics today, I can say we are following up, reversible or reversible. Okay. In that, I can say the process with respect to non-flow, we can say is an isobaric process, isobaric process, isothermal process, isotropic process, then polytropic. Accordingly, the change in entropy refers to because the function of change in heat transfer. So isochoric means volume constant, isobaric means pressure constant before and after the process, isothermal means temperature constant, isotropic means entropy constant, polytropic means nothing is constant, it follows the law V power n equal to constant, where n equal to 0 to infinity. When you say n equal to infinity in polytropic, it is called constant volume process. When you say n equal to 1, it is called isothermal process. When you say n equal to 0, I can say it follows a constant pressure process. When you say n equal to gamma, it follows the isotropic process, PV power. Clear? There are several processes happening. Whereas for to heat the water, right, to convert the water into steam completely, right? That is called constant pressure process or constant temperature process, we can say. There is no change in temperature, there is no change in pressure. So only your amount of heat you are providing to water, maybe in the range of 2330 kilojoules per kg of water, I can say you can able to find it. So these are the basics. So branch of chemistry deals with energy exchange, entropy and spontaneity of a chemical process. Enthalpy is the heat absorbed by system during constant pressure process. So you can say, if you want to really prove that, we all know that from the law of conservation of the first law, Q is equals to W plus. I can say for other I can say, maybe we can put del E, change in energy. This is the from the first law. Say, assume that the process is happening, the constant pressure. So in order to find out the Q integral, I think you know the integral PdV. So by applying here, if the pressure remains constant, that means V times V2 minus V1. So V2 V2 minus V1 V1. That means MR times V2 minus V1. Okay. So that is W. Maybe you can say except the internal energy, other forms of energy are assumed to be zero. You can take del E equal to del U. You can say it's nothing but MCV delta T between 1 to 2. So MCV T2 minus T1. So if we submit both the things, we can say R is nothing but Cp minus Tv, gas constant is Cp minus Tv. So we can say Q is equals to MCP T2 minus T1 minus MCV T2 minus T1 plus MCV T2 minus T1. So this cancels. Finally, you will get Q is equals to MCP delta T, which is nothing but enthalpy. For a constant pressure. Okay. So enthalpy, the constant pressure process nothing but heat. So if you maintain the pressure remains constant. So how to find out the heat is? You need a temperature difference using thermocouple to find out. So see heat depends on the fluid. You can find it. If it is water, 4.186. If it is air, 1.005. So given mass, you know that find out the heat, which is nothing but enthalpy. Okay. Enthalpy and entropy play a crucial role in process spontaneity. Spontaneous process proceed without any outside assistance. Okay, so it will happen automatically. Temperature and pressure may affect the spontaneous process. So you can see here the good examples are, I can say. So when it is evacuated and you have the same pressure, I can say it is not non-spontaneous if you maintain the same pressure. And if you say the pressure difference are very high, if you open it automatically, the process is going to be non-spontaneous. Spontaneous process, the examples are process that are spontaneous at one temperature, I can say be non-spontaneous at other temperatures. Above 0 degree, it's a spontaneous for ice to melt. Below 0 degree, the reverse process is, I can say, spontaneous. So here you are going to provide the heat to melt the ice into water. Similarly, you have to remove the heat to convert the water into ice. Both are spontaneous. It's a naturally occurring process. So gives you free energy. Free energy refers to the amount of energy available during a chemical reaction to do cellular work. The free energy concept was developed by William Gibbs in 1870s. The Gibbs free energy, the following perspective is exergy. The Gibbs free energy is a thermodynamic quantity which can be used to determine the reaction is spontaneous or not. This is the reaction. So entropy increases or not, we can able to find it for any reaction. So for ammonia dissociation into hydrogen, I can say you are going to provide the heat from the surrounding. So it's an endothermic process, right? So it's an endothermic process. So fewer restrictions. Only I can say this is stable actually. Ammonia is stable. This is a non-stable products. Okay. So if you want to convert the stable into non-stable, you have to provide so much of energy to break the 3 bonds present in the nitrogen. Okay. So you can easily combine N2 and 3H2 N2 and hydrogen to form ammonia. Similarly, you can put a lot of energy in, I can say, to dissociate it. So one is maybe spontaneous, another may be non-spontaneous. So gives free energy. You can see here for any reaction, we can able to understand whether the process is happening in equilibrium state or I can say spontaneous state or non-spontaneous state. We can able to identify from the Gibbs free energy. The Gibbs free energy negative, the forward reaction is spontaneous. The Gibbs free energy is positive, the reaction is spontaneous in the reverse direction, opposite direction. If Gibbs free energy is zero, that means it attained the equilibrium. We say, suppose you want to bond the hydrocarbon free to form carbon dioxide, hydrogen, and water vapor. Also, we can able to find out and during the forward reaction whether you are going to get a negative or you are going to get a positive Gibbs free energy. Accordingly, you can say whether the forward reaction is spontaneous or the reverse reaction is spontaneous. Suppose you are getting delta G equal to 0, it's nothing but H minus delta T times delta S. If equal to 0, that means it's equilibrium. So attain equilibrium. So it is very difficult to go for a reverse process. So the total ammonia generated globally was estimated approximately, I can say, 179 million tons in 2020. So 40% increase of the population growth, I can say, increases means naturally the fertilizer used for increasing the crop yield is also increases. The population growth is directly proportional to the, I can say, amount of ammonia consumption. Ammonia process can be divided into three types: green, blue, and grey. As you all know that for producing green ammonia, we are using what is called green. No energy from the green comes from the conventional source. Blue means okay, you are going to consume the energy from the green, but CO2 can be captured. Grey means okay, we are going to consume the energy from the green by using conventional energy sources, but CO2 is not captured. Okay. So now recently, green ammonia has been used as a clean energy carrier in marine industries. Then cracking the nitrogen tribonds require high energy, 80 kilojoules per mole. The mechanism for reduction of nitrogen into ammonia is a complex process. Therefore, different theoretical analysis approaches have been taken to understand the reaction mechanism, which has been validated by different experimental techniques. So this is an introduction related to the today's presentation. The catalytic materials first participate in forming unstable radicals as an intermediate step. So, as I already mentioned in the previous lecture, the catalytic material what we are going to use is going to find out the different pathways. So, what is the minimum energy you need to provide such a way that the required products can be attained? Okay, so that's called lower activation energy. So, you can find out the minimum energy in which the process is going to happen. So, that will reduce the energy consumption for converting the hydrogen into ammonia. Okay. So any process with catalyst and without catalyst, always without catalyst the energy consumption is going to be higher. With the catalyst, definitely there will be a drop in the energy consumption because you are minimizing the amount of the energy needed for either for forward reaction or reverse reaction by adding catalyst. So where these catalysts are commercially available, particularly for ammonia formation and I can say dissociation of ammonia. Ruthenium, ferrous, nickel, cobalt, nitrite have been investigated for Haber-Bosch ammonia synthesis process as well as green ammonia synthesis. So our intention is supposed to be these are already proven, right? These are already proven catalysts. So we need to find out some new catalyst or from the I can say from the available material in the periodic table or from the material we are going to collect it from the different waste sources, right? The e-waste or whatever the way the products in these materials are present, you can convert it, you can collect it and convert it to catalyst. You can able to break down the I can say the process cost. So there is always people talk about the thermodynamics versus chemical kinetics. Thermodynamics tells us if a particular reaction will be spontaneous, but not how fast it will occur. So whether the process is going to be spontaneous or non-spontaneous, we can able to identify from the Gibbs free energy. But from the chemical reaction, how fast we can say it's going to occur, that you can find it from the chemical. So we can able to identify from any forward reaction or reverse reaction from thermodynamics perspective whether it's spontaneous or non-spontaneous or equilibrium. But how fast you can able to, whether the spontaneous process happens, how much time taken to complete the spontaneous process, you can able to find out from the chemical kinetics. So chemical kinetics, I can say, used for understanding how chemical reactions, the speed of the reaction, time taken for by reaction to reach equilibrium. So always we are talking about, I can say, the equilibrium. So in terms of the body hydrocarbon field, we are saying that when it reaches carbon dioxide and water vapor, it's equilibrium conditions are attained. Right? It may not be, I can say, create any issue, or I can say in terms of the reactants and the products. Suppose we are coming out with the products like CO or oxides of nitrogen. You may not think that CO is going to be remain same as CO. Oxides of nitrogen is going to be there remains as NOx forever. But the CO2 formation, water formation happens spontaneously, but it will also CO and NOx will form nitric acid after some time, or CO will form CO2 after some time. But that we cannot, I can say. The time in which the formation happens of CO2 and water vapor will be immediate, but other products of combustion, it takes own time for forming the products. Okay. So here the kinetics, you find out the rate at which the process is going to happen. Okay. The reactants and the products. So for the reactants, no, during the reaction, I can say there will be a lot of energy is going to be absorbed. Then it will be, once it's stabilized, it comes to the products. So the activation energy, I said already, the energy, minimum energy you need for aiding the reaction, whether it is with the catalyst or without catalyst. So you need to find out the activation energy for any process, and you can able to, I can say, conclude that what may be the catalyst I can able to use it to have the, I can say, reduce the activation energy. Suppose for a process of forming ammonia, the consuming 80 kilojoule, 80,000 joule of heat you are going to consume for producing 1 mole of ammonia. So you can find out the way in which you can able to reduce the energy consumption of 80 kilojoules to 40 or 30 or 50. That needs to be studied by going for finding out the activation energy for using that particular catalyst. So you can use different catalysts to find out activation energy of the products of the ammonia and find out which is going to be consumed minimum energy that you can use as a catalyst for the Haber-Bosch to get the desired products. You can see here the reactants, the products. So without catalyst, you can say this much amount of extra energy was provided. Shown in the yellow color, the dotted line. So without the products of ammonia, we will get this much energy. Suppose we are using some kind of catalyst which has a fine short path, which consumes only lesser energy, then that is nothing but a catalyst reaction. So non-catalytic reaction is catalytic reaction. Always catalytic reaction reduce the activation energy by at least 40 to 50% of the energy given. So ammonia Haber-Bosch system. So nitrogen reacts. Normally, I can say why we are not, I can say, using the same ratio 1:1 for both the case. If you are using the 1:1 reaction, then reverse reaction is possible. Reverse reaction is possible. Suppose we are using 1 mole of nitrogen and 1 mole of hydrogen, then ammonia formation happens, then ammonia will be immediately dissociated into nitrogen. The reverse reaction is not going to be controlled. Whereas if you increase the, I can say, hydrogen 3 times the nitrogen, then it will be very difficult for the reverse reaction because our ultimate aim is to produce ammonia, not to dissociate ammonia and nitrogen again. Whenever is necessary, you can do it. But for fertilizer, we want only ammonia. So here the process, the volume ratio 1:3 they have used. The temperature is a Haber-Bosch process. So we are producing the ammonia, you can cool it and it will sold in the form of liquid. Unreacted nitrogen and hydrogen can be again sent. So here they are using ferrous with the, I can say, the bond of 1:1. So here the Haber-Bosch reaction for one cycle, there are they are claiming that 26 intermediate states are happening before forming ammonia. So that's called intermediate reactions. So from nitrogen reaction to ammonia to breakage of nitrogen and breakage of hydrogen, it forms different compositions in between. This is the first reaction. Assume that the final reaction is the 26th reaction. In between, you have 25 reactions. So the intermediate reaction, we are not going to bother about it. Ultimately, we need only the product in the form of ammonia. But it's not formed immediately from nitrogen to ammonia. So intermediate states are. So quantum mechanics is to predict the reaction mechanism and kinetics of for ammonia synthesis. The best ferrous single crystal surface. So this is a proven catalyst. So it is going to rule for several years. It has so far no other catalyst having the I can say minimum ignition energy to produce the ammonia from the upper portion. So people start working on different catalysts, maybe ruthenium, nickel, platinum. They have tried, but for us, Fe2O3 is going to be give better yield than the I can say other type of catalyst because why they are claiming I can say more yield is the activation energy for this kind of catalyst is going to be lower than the other type of catalyst. So they have to find out the kinetics, I can say, and this mechanism. They are using a Monte Carlo model to predict the steady state rates of all the reaction steps to obtain the turnover frequency for single crystal experiments at 600 around 500 Kelvin degree centigrade at 20 atmosphere. Okay. So reaction mechanism. They are as we are mechanical, we are not much aware. We don't want much. I can say knowledge in I can say kinetic mechanisms. But whereas if you belongs to chemical or chemistry, the people are more focusing on using some kind of model to predict what are the different reaction mechanisms are involved, reaction rates are involved. So they are working on. So ammonia synthesis with respect to temperature, so I can say the maximum concentration versus temperature. You can see here the high speed. I can say high speed, low equilibrium, high equilibrium and low speed. So they are going to get the maximum ammonia concentration at the temperature of 350. You mean to say that increasing the temperature to higher level doesn't mean that it's going to, I can say, that equilibrium at a very faster rate. Okay, so you need to optimize the condition, pressure and temperature in such a way that you will get a required product. Okay, so each catalyst will behave at particular temperature. So ammonia synthesis chemical equilibrium. So here 1 mole of nitrogen, the green circle shows the 2 I can say mole of I can say nitrogen. That's nitrogen bond I can say 2 N. Then the light I can say gray. There are two circles are there belongs to nitrogen. It forms 2 molecules of ammonia. You can see here 28 grams of nitrogen reacts with I can say 6 gram of hydrogen, ultimately we are producing 34 gram of ammonia. So ammonia synthesis is an equilibrium limited exothermic reaction at relevant reaction conditions, and it is occurred that the synthetic gas must be free of any reactive contaminants that poison the gas. So as I already said, so it is working the principle of I can say during the exothermic process. So the hydrogen will be absorbed on the catalyst porous surface. So we need to ensure that the desorption of the absorbed hydrogen going to happen frequently. Otherwise, it's going to, I can say, some pores will be closed. It will affect the ammonia formation. So it will ensure that the regeneration of the catalyst is happening at a particular temperature and then under pressure. So regeneration is very important concept for ensuring the yield of the ammonia. So there are different reaction rates are available suggested by Temkin and Langmuir and Ozaki. So based on their I can say the kinetic communication, you can able to arrive the reaction rate. So ammonia synthesis chemical reaction mechanism over ferrous catalyst they have mentioned that. So energy how much per kilojoule per mole they are providing to form ammonia. So about I can say 1124 plus 14. So the total energy they are supplying here to form the intermediates, different intermediates are forming to form ammonia finally you are supplying about 1150 kilojoule of energy per mole to form ammonia. So here in the ammonia you will get the energy level of 460. That means about 1/3 of the energy your supply is going to be, I can say, it's not considered for forming the ammonia. There are intermediates which are consuming the energy. So 2/3 of the energy was supplying at the Haber-Bosch reactor is not utilized for forming. So that's how that means 2/3 of the heat is waste. So different molecular structures of intermediate species formed before it forms the, I can say, ammonia. It is given in the, I can say. So when it crystal surface, you come across the undergraduate, okay, 111, 210, something. It talks about different IPCC, FCC, different the structural element they are talking about that. So produce ammonia over different, I can say, crystals and corresponding structures. So accordingly, I can say you can able to find the different structural things also by using some kind of change. Ultimately, here they are claiming that maximum ammonia is going to be formed for ferrous structure of 111 at a temperature of 400 degrees centigrade, then the pressure of 20 atmosphere, then the ratio of 3:1. So the ammonia from the electrochemical method, I can say, we are using the methane as a constituent, then by using electrochemical method, right, how the ammonia can be formed. So here, along with ammonia, like the products of CO and CO2 will be coming up. When it's CO2 combined with water vapor or in steam, produces carbonic acid also. That is going to be then other issue if you are dealing with hydrocarbons as fuel for producing the ammonia. So you can go for air boats or you can go for electrochemical method. Methods are available, but it depends on the required quantity or output of the ammonia you can use it, because you cannot go for electrochemical method to produce few million tons immediately. It takes more time. In terms of, I can say 100 kg per day or maybe 1 ton per day is possible. But in Australia, I can say in Russia, Japan, people are already started working on million tons capacity, but it's not commercialized till now. So plasma technology, we already discussed this thing in our tutorial in our laboratory. So the rate determining the step over the possible ion catalyst for ammonia synthesis can be proposed as follows. Suppose we are going to use some kind of the catalyst what they are using Haber-Bosch for ammonia, I can say, formation from the plasma energy. So they proposed, I can say, as follows. The nitrogen dissociation rate determining surface catalyst reaction at the adsorbed species. Then ammonia desorption reactions. So the rate determining the step over the possible ion catalyst for ammonia synthesis. Right, one of the paper they have proposed in this way. Nitrogen dissociation, absorption in the ammonia synthesis rate determining step as demonstrated by the various experiments. So in the process of accelerating ammonia production, non-thermal plasma also involved in, I can say, producing the ammonia. So there are so much of intermediate species also coming out during the reaction. You can see here. Yesterday, we spoke about, I can say, UV, how it's going to involve in the ammonia synthesis process. UV or plasma energy or microwave, as Professor already mentioned, that micro catalyst system. So we need energy in the form of different sources. That's all. Maybe UV, another maybe microwave, and even radio frequency. There are many ways you can able to produce the heat, but the intensity of energy comes out from the given minimum energy. I can say the microwave and the plasma is going to, I can say, leads the formation of ammonia. So plasma-based ammonia synthesis, we are using different, I can say, catalyst for the plasma synthesis process. So we are going for thermal catalytic ammonia, plasma catalytic, thermocatalytic ammonia decomposition. So these are the things we have discussed in many lectures. And Haber-Bosch is simply, I can say, thermal catalytic ammonia synthesis process. What we have used in our research purpose or for the demonstration, what we did is the plasma catalytic, I can say. It's not catalytic, plasma ammonia synthesis. We learn to bring the catalyst into it to enhance the ammonia formation. The thermal catalytic, I think I can say, is similar to, I can say, the Haber-Bosch system. So we are going to use the energy in the form of heat to decompose the ammonia into nitrogen and hydrogen. For that, the catalyst is also placed in it. So when I am discussing the catalyst, I said there will be a homogeneous and heterogeneous catalyst, and gas phase also. There is a possibility of, I can say, you can gas kind of catalyst also you can use it. How the reaction happens to form ammonia, they have discussed in the schematic that maybe you can say is that the reaction mechanism they have incorporated in that one of the paper. Then we have so gas phase absorption, diffusion, then the excited state, inhibition, enhancement. These are the process happening now to form a product. So different, I can say, way of producing ammonia from hydrocarbon. So reduction, oxidative reaction by using aluminum oxide or aluminum nitrate. One of the paper we found that, and they are using aluminum oxide. When it reacts with the carbon, produces, I can say, carbon monoxide. That the carbon monoxide, I can say, it comes as a product. When it comes out in the form of, I can say, forming the ammonia. So here the water is used for oxidation by using aluminum nitrate. So the ultimately we are going to produce the. This is something like two catalysts they are used for reduction and oxidation. So reduction means we are breaking out the, I can say, nitrogen. Oxidation they are going to combine. So there are different calcination you need to use for chemical calculation energy or reaction rate or chemical kinetics. So here they use the hydrogen to nitrogen ratio 1:4, right? Plasma power of this one. Then they found that what the best rate in which the ammonia can be formed by using the zero kinetics. So ammonia decomposition based on hydrogen technologies, right? So there are different technologies are available. But thermal decomposition, I said, right? Energy, you want only heat. So you can either produce from the resistance heating, electrical heating, or I can say micro heating, or induction heating, or solar energy, or combustion. But I need that temperature and pressure. So you can provide that temperature based on any mode of, I can say, the device. So the ammonia carries 17.6% weight in, I can say, hydrogen in the ammonia. Easy liquefaction, ammonia having a very, I can say, easy to liquefy at a 9 bar at a temperature of 25 degree. Or you can keep at 1 atmospheric and minus 30 degree, you can liquefy it. Excellent obtainability, safety and high technique for maturity. So non-thermal decomposition, right? So here we are going to provide the thermal based of, I can decomposition of ammonia. They are going for non-thermal based, particularly photocatalytic way of, I can say, producing the decomposition. They are using the plasma technology or electrolysis or photocatalysis. There are the three technologies that they are using for dissociating ammonia in non-thermal mode. So here another one you can make use of some kind of the membrane impregnated with the catalyst. Also you can able to, I can say, decompose the ammonia into hydrogen. So hydrogen here high in terms of mass basis. It is the highest calorific value fuel, but in terms of volume basis, it's the poorest calorific. So ammonia is the average calorific value when compared with petrol oils. So research, what exactly we need research? Research is focusing on novel catalyst materials, including metal nitrates, carbides, and lithium-based catalysts, as well as electrocatalytic and photocatalytic system to lower energy. So our ultimate aim is how best we can able to produce the maximum ammonia, either in the form of consuming minimum energy and catalyst also added to the minimum energy consumption device like microwave or I can say induction stove or induction energy or the plasma energy. Then further adding catalyst in that system is also reduces the energy input for producing the ammonia or decomposing the ammonia. Water plasma catalyst is also a promising approach, providing unique activation energies to facilitate ammonia formation at mild temperature. Already, we are producing ammonia at 1 atmospheric pressure and temperature. I can say the normal ambient temperature. Still, you can able to, I can say, minimize the plasma energy to some level. We can use the catalyst from the quantum plasma technology. We can able to increase or keep the same energy level, increase the ammonia yield by using the catalyst, or keep the, I can say, same yield, minimize the energy consumption in the terms of high voltage or minimum current. Then we can able to maintain the same efficiency. Plasma-assisted ammonia synthesis is gaining interest as a suitable alternative, but the reaction mechanism and plasma liquid interface are complex, not yet fully understood. So that is the scope for I can say, people working in this area. So plasma, we can say they are producing ammonia within minimum time. Reaction rates are very high. I have minimum activation energy needed, with including the catalyst also. Further reduction in activation energy is also possible. But how it is going to form from the water into, I can say, hydrogen, then reacts with the nitrogen. How the reaction happens, still it's a complex process, it's not fully understood. So you need to bring some kind of model, right? Or Monte Carlo model or something, we have discussed earlier. So we can use this suitable model to understand the behavior of the, I can say, kinetics. Factors such as electron energy distribution, ion molecule collision, and radical formation need detailed study. So we are simply saying energy comes in the form of plasma, but you will go in depth in analysis of which exactly contribute for giving the high intensity energy in the plasma. So electron energy distribution, ion molecule collisions, and radical. So you need to go for, I can say, the computational study to ensure that how which energy is going to be plays a major role in bringing the high intensity energy. Advanced spectroscopic methods like FAR and mass spectroscopy are being used to observe the reaction intermediates and pathways. The problem in India is only, I can say, we have the systems at one point, we have the FAR and the mass spectroscopy and somewhere. So we need to take the sample and take it for analysis. But we go and see in, I can say, good research labs in India and abroad, every system, every reactor is attached to all the equipments. There is some online measurement, FTIR, GC. So I have visited, I can say, Brazil, UFRJ, University of Rio de Janeiro. I found for every reactor, then FTIR, GCML, then I can say whatever may be there, the normal spectroscopy, all those things are attached to the particular reactor itself. So they are online, they are monitoring. So that type of environment needs to be created to, I can say, to analyze the reaction, I can say, during the process itself. I already said kinetic modeling combined with exponent insights also your priority to optimize the condition and improve the reaction yields. Computational modeling and machine learning tools are increasingly being utilized to predict the reaction kinetics across different conditions. This data-driven approach allows for faster identification of optimal process parameter, reducing the need for costly pilot. So as we have already discussed that one of the tutorial, there are several parameters I can say, for particular process involved in the product yield. So need to optimize the process by using some kind of machine learning process or data maybe data handling tools. So one of the thing, people are using design expert and the MATLAB artificial neural network. Similarly, there are many things we need to explore it, particularly for for certain kind of applications. We need to find out which, I can say, tool is going to be give the best results on the R square value. The research on decomposition of catalysts that work efficiently at low temperature is essential. So people start working on decomposition at ambient temperature, what type of catalyst they can able to, they are going to use it, so they are exploring it. Efforts are also focused on developing certain catalytic pathways to avoid undesired byproducts. So we need to sometimes, right, the usage of catalysts, reducing the activation energy and finding out the different pathways, but unwanted products needs to be avoided. Along with the ammonia, some I can say toxic products are coming out that needs to be studied before, I can say, commercializing the particular catalyst for the ammonia generation. Hybrid systems combining catalytic and non-thermal plasma methods may offer pathways for rapid and on-demand hydrogen release from ammonia. So dynamic models of ammonia kinetics are essential for integrating synthesis process with renewable energy, allowing the system to adjust to fluctuation in energy supply. Energy efficient processes like electrochemical ammonia synthesis are being explored, which can directly use renewable energy. Ammonia kinetic research is evolving with innovative methodologies and advanced computation tools, bringing the promise of greener, more efficient ammonia production close to reality. Okay. So these are the references I have used for preparing the PPT. So I thank my scholars for helping me to prepare the PPT. Thank you. I think you can explore important papers provided by doctor.